Great pleasure to be back here. Right, so what is good? First of all, apologies, I don't have a paper yet, I don't even know how to write this paper, so your comments will be very important. Alright, but we have an idea, we have an identification result, which is the main thing that I'm going to present. The application is not very well developed, Monte Carlo is okay, and the statistics, of course, the inference depends on what model you choose. For a spatial model it will be different, but as you will see, the identification result is not anything specific to the spatial domain. The same identification works for many different endogenous systems. In particular, the identification is very closely related to structural power models. Right? But enough of that introduction. So here is where I come from. Right, chicken and egg. Why chicken and egg? Well, those starts from Aristotle, as far as I can see. Basically argued that so the question is sort of meaningless, essentially. So if there was a first chicken, it must have grown out of an egg. If there was a first egg, it must have come from a chicken. So the question is. Then we have Hegel. Hegel's point was that, well, not that this question is not interesting, but more interesting question is what is the the dialectical relationship between chicken and egg. And in economics, what we typically do is that we try to take the Hegelian view and we write down a structural model in order to understand the endogenous relationship between the chicken and egg. I say chicken and egg, it can be the spillovers between regions, it can be money output prices, it can be anything. So, but that is how we write down a model in economics. But very soon what we do is then we make some heroic assumptions to estimate the structural, deep structural parameters. Right? And typically one of the assumptions that we make is a recursive system. And this paper is about that recursive system. So this same thing holds for the recursive system. We have had discussions regarding this earlier today. Schmidt, Nevi, that's work by Kavinian and Kruka. Similar, the model is very similar to macro models as well. Money output prices, well order your markets assumed by neoclassical theory. Who told us that is the particular order in which markets clear? Nobody. So question is, if you have data, can you figure out which is the chicken and which is the egg? You have data and you know that there is a recursive structure. You have several regions through which shocks move contemporaneously. Alright? Can you then say where it originates from and where it ends? Okay? And we are going to find out that under certain conditions that is true, under certain models, so that is what this identification result is going to be about. Okay. Alright, I'm not going to go into this, but this is a humorous thing anyway. Alright. So that is the chicken and egg in an endogenous structure. What happens in the spatial domain? In the spatial domain, this question is a bit difficult in a way, because as opposed to, so we write down time series models and we motivate our spatial models using time series models. So time series models have the property that time moves only forward. The past affects the present, the past and the present affect the future. In space, we do not know how information flows between regions, and that is precisely the problem with space. Alright? However, people often use triangular or recursive hypothesis. One very common one from the British context is this phenomenon of ripple effects. Apparently, price shocks originate in London, then move progressively towards the northwest, towards Manchester. This is an assumption. Can you figure out this recursive structure? Suppose there was a recursive structure, can you figure out the ordering from the data? Is the question. Right? Okay. So let us first of all do a very simple thought experiment. Okay? To show that this problem may not be that meaningless. Okay? So let us say we have two cities, live in Edinburgh and this is Glasgow. Okay? Two neighboring, close by cities. Let us say that the shocks move, or so whatever, house prices, let us say Y is house prices in Edinburgh are not affected affected by house prices in Glasgow, but house prices in Glasgow are affected by house prices in Edinburgh. This is an example of a recursive system, right? This is a spatial autoregressive model where the weights matrix is like this. Okay? The question we are asking is, suppose we knew that there was a recursive structure, but we didn't know whether the W was here or the W was there. Can the data tell us where it is? Right? Simple thought experiment. In this case, suppose we make the assumption that these idiosyncratic errors here have the same variance in the two regions. In that sense, it is homoscedastic. Then which one has the larger variance? Well, obviously Glasgow, because for y of Edinburgh, there's only this error of Edinburgh. Whereas for Glasgow, there's the error of Edinburgh plus something coming from, there's the error of Glasgow but something coming from Edinburgh. So the variance is going to be larger. And so, just by ordering of variance, we can figure out which one comes at the top of this causal ordering channel. Does this intuition hold when we move to multiple regions? Well, we are going to find that out. But before I do that, let me do the following. Let me take this chicken and egg story literal, because some people have. In 1988, Thurman and Fisher wrote a paper in the American Journal of Agricultural Economics asking the question, does chicken cause the egg? And they look at data of egg type chicken and egg production in the US over several years, and they ask a question of Granger causality. 2 points straight away to make. We are not talking about Granger causality here. We are talking about Rubin causality. We are talking about contemporaneous ordering. Okay? The second thing is, of course, their results are wrong because they ignore non-stationary. But that's a minor point. That does not really affect us. But let us say we write down sort of a spatial VAR model in this case, the simple case. So yt is y chicken and y egg. Alright, so that is my vector. I have a spatial var. So we have a spatial var, yt is equal to alpha plus wyt. Remember, in our world, w is unknown. So the spatial autoregressive parameter is not there, right? Because it's not identified separately from w, right? This holds with any spatial model where w is, object of inference. Alright, so that is wyt plus a lag. So this is the var, okay, and an error. W we know is either this or this. Okay, I've already started relaxing the assumption of homoscedasticity. So my error term here, okay, is a diagonal matrix. Of course, all spatial dependence have to come through this W. That is the assumption that I am making. They are independent, but they can have different variances. Alright? So if I write this down in reduced form, I have I plus W alpha, I plus W. Why do I have I plus W? Well, this is the other thing which is very interesting. If you have a triangular W, then W squared, W cubed, any higher powers are 0. So I minus W inverse is exactly equal to I plus W. Alright? So this is I plus W, and an eta t, and eta t has this one. Okay, so this is the reduced form error. Write down the variance covariance matrix of this reduced form error. Okay, so that is this one. And what I then do is I do a singular value decomposition of this variance covariance matrix, from which I get the relationship that this is the diagonal matrix of eigenvalues, square root of that times the eigenvector is exactly the same as this one. Alright, so that is, well, that's one of the results. Okay? Alright. How does this help us? If you look at this matrix carefully, you will find that the diagonal elements of this matrix are exactly sigma 1, sigma 2, so on. Sigma chicken, sigma egg, so on. Alright? So I have chicken and sigma egg just from a reduced form, estimation of a reduced form var. Okay? If I get that, what I can now do is I can scale my original variables by these estimated guys, sigmas, and then I'm back to the homoscedasticity assumption, and then I can use the identification result to figure out whether the chicken comes first or the egg comes first. Alright? So that is the simple analogy. So reduced to homoscedastic case. So these are our error standard deviations. Okay, using the data, I estimate this as this, and then I can just write this down in scaled form, and the reduced form is very similar to what we saw earlier. This should be W star. So it has the same structure. Okay, so we can infer on the structural order. Once we have inferred on the causal order, then we can estimate a structural war model, and this is my estimate of that structural war model. Okay. Now, therefore, I find that, remember, chicken was first, all right, and egg was second. So contemporaneously, egg causes chicken, and in a Granger causation way, chicken causes egg. Alright, so that is the answer to the question in the chicken egg story based on the chicken egg data. Right? Okay, so far I had only two regions, or two entities. So now I am going to generalize this to a multiple region context. Okay? Alright. A bit of background now. So what does this relate to? Well, this also relates to the now going substantial literature on an unknown weights matrix. One of the things that we know from this literature, well, there are two things. One, which was pointed out earlier by Paul, for example, so it's very important to keep your view very open if you want to really capture the direct and indirect effects very well. That is very important. Persistent joint equilibrium effects emerge if you allow that. And also it can often explain this factor of negative spatial correlations in small local spatial scales. Alright, what do we know? What we know is that in a model, whether that be a spatial autoregressive model or a Sarar model, spatial error model, let's put it this way, okay, if we do not know the W, and want to estimate that from the data, this econometric problem is only partially identified. You can only identify about half of W. Okay? And the symmetry, if you assume symmetry, then you can identify the whole of W. Basically, you can identify half. So if you have a triangular or a recursive structure, you will be able to estimate that. Okay? Question here is not that. It is about identifying what comes at the top of the triangle and what comes at the bottom. Okay, there are alternatives to the symmetry assumption, moment conditions, sparseness of W. We have had discussions regarding both of these. Lungfei discussed this earlier today. We have some work in this domain as well, and then there's increasing domain of weights matrix. So there are different ways of Avimanu's work was in this area, PhD work. So all of these come within this same general context. You need some structural assumptions to identify the W. Our maintained structural assumption here is an assumption of recursive structure. Okay, 3 regions. Just going to show you this and straight away show you some results. Okay, so 3 regions. How do you identify? Well, the one which comes first is the one with the smallest variance. Then you partial that out from the conditional, you partial that out from the autocovariance matrix and look at which one is the smallest, that is the second, and so on. So this analogy holds for multiple regions. Alright, so this way we can identify the full ordering for a series of regions. Okay, series of regions. Alright, Monte Carlo, how does it do? This is some Monte Carlo experiment with 9 regions with both positive and negative spatial weights. This is a spatial error model, but very similar things will follow with a spatial autoregressive model. Remember that in this world, when where W is unknown, it is very difficult to separate the spatial error model from the spatial lag model. In general, it's a hard problem, but okay. With n equal to 9, with replications, 500 replications, that's quite a lot, right? With 500 replications, you can identify the full correct structure. Okay, so I showed you the identification result earlier. That is only identified 6.4% of the time. Having said that, 6.4% is still much, much larger than 1 divided by 9 factorial. Okay? Right. If you went to 1000 replications, that is 26.2. Okay, so it just shows you the amount of data which is required to do this in real life. But the identification result stands. Okay, so we can do inference using Bootstrap. This is just showing that the diagonal of this matrix there, that I talked about earlier, is simply the sigmas. That is what you can use for scaling. Here are the results. What do I want to say? So the maintained assumption, the main assumption is recursive structure. There is no other assumption. The assumption is that there is a particular ordering of these variables for which W will be lower triangular. Okay, so that is the only assumption. Important thing, which is very important here, is this thing that I was talking about earlier. This result is extremely important. Okay, so I minus W inverse is I plus W. And then the results, basically, well, I've shown you the general idea of the results. Okay, 1 minute. Okay, all right, very quickly. This is very hot-baked, but a quick application. The ripple effects hypothesis in the case of Britain, seasonally adjusted house price indices, okay, from Q4 1973 to Q4 2013. These are the regions. Okay, so there's the London and region around London and the rest of UK. All right, Scotland is always outside the map. That's not included there. We do panel eliminator tests, make things stationary, and so on. Once they are stationary, then we ask the question of causal ordering. This turns out to be the causal ordering matrix. What else is there? We have the lag. Okay, we include the lag. We include a factor structure to account for spatial granularity. So strong dependence, essentially. All right, we have fixed effects. All right, the results are a bit sketchy at the moment, but it seems that the shocks originate from West Midlands and have influence across the UK. All right, then causal ordering moves to the London suburbs, but London, central London, inner London comes much later. So that's about it. Okay, so so thing is that triangular recursive structure. Estimation is easy, if ordering is known. Ordering can be inferred under homoscedastic errors, but if errors are heteroscedastic, model can be scaled using plug-in estimator of standard deviation. Monte Carlo performance is reasonably good, and this is reasonable. Thank you. Thank you very much.
Just two questions about spatial causality. In fact, identifying spatial causality from panel data often require to consider spatial interactions that are relatively stable over the time. How to diagnose is a good idea with my data. For example, for numerous relationships, like for example, employment and population, it seems clear that at small scale, at small number scale, causality is a ping-pong game. And in some place, in moments, employment for people, and it could be the opposite next time after. And spatial causality could be itself a spatial process. So how to diagnose with my data that is perhaps linked to the question of stratification and how to choose the time, but the time could be different, the period could be different in the place, so it's itself a spatial process. It seems very complicated.
Oh, all right, okay, so you want my response? Okay. Yeah, that is precisely the problem. That is not to say that your measured W matrix is in any way better. You are even more ignorant in that case, right? So you are making more assumptions. Here we are trying to strip down the assumptions and try and see what assumptions you require for identification of the W. Okay. If your theory does not suggest recursive structure, maybe it suggests symmetry. There are methods available for symmetry. Maybe it suggests core-periphery model. There are methods available for core-periphery model. The question is to extend the horizon to situations where W can be inferred on, and different methods or different structures will work in different situations. Thanks.
Okay, maybe one question. No?
Maybe one. In your application, you show, for instance, you've got a triangular weight matrix, and you can see that, I mean, London, the London city is fully in the bottom world. So this means that many cities will affect London, but London will affect few cities. I would say that in that sense, I would put London as the leading one, because all the columns of London should be full, because London will affect all of the countries, all of the cities, all of the areas, whereas it won't be affected by many areas. So my question would be, how sensitive are the results you found with respect to the order?
Okay, so there are two answers to the question. The first answer is, with 500 replications, we recovered the correct structure for 2.6% of the cases. So that is the amount of data that you require to recover the correct order. Number one answer. Number two answer, when you say that inner London should be at the top, who lives in inner London? The Queen and Roman Abramovich. Does that affect the rest of the island? Well, it's a question that one has to ask oneself, right? Outer London areas where real people live, they are at the top. Okay, so they come at the top of this causal order. So I don't think that is, kind of so outlandish. But again, the point is that you have to make assumptions. Structural identification requires assumptions. Not avoid. That is the new chicken and egg story. Let's put it this way.
Thank you very much. Thank you very much. So the next speaker is Guillaume Gillon from INRA. So the title of the paper is Spatial Econometrics Models under Specification. The case of spatial covariates and spatial specification. And this assistant will be Michaela Cristina from the Polytechnic School Zurich.
Thanks. I represent John Moore with Davide Martinetti. So this paper is about misspecification in spatial econometric and how to deal with spatial autocorrelation and spatial heterogeneity at the same time. It's an emerging question and important question nowadays in spatial econometrics. And my talk will also be related to identification of W, but not in a context of panel data. The presentation starts with a list of data generated processes that consider spatial autocorrelation and spatial heterogeneity for different sources of misspecification, followed by a short overview on the spatial econometric estimators that can deal with such DGPs. Then we turn to design and result of a Monte Carlo experiment and a quick comparison with a recent paper with similar approach on real data about house pricing and conclusion, and if I have enough time. Let's consider the SAR model with an endogenous spatially variable, spatially autocorrelated, assuming linear dependence of YE with its neighbor simply implies there exists a set of non-null lambda YEG and we can rewrite the model as in more general form. And the hypothesis that we can identify lambda ig with a single term lambda w with a non-interaction matrix w that specifies the relationship between each observation. It's very practical because it simplifies the estimation, but it's very restrictive. And we can see how to go beyond that. And there is three issues that lead us to explore a model in which we have both spatial autocorrelation and spatial heterogeneity. First, you have to deal with two screens. In fact, there is no definitive indication for base choice of W in econometrics. Even with a proper specification of W, the interaction between neighbors may vary over space in intensity or in structures. And the SAR model can be viewed as a constrained spatially varying coefficient model in which beta UEVI, where UEVI is the coordinate of the location, equal lambda W beta. In the paper, the biggest myth in spatial econometry, Kesagen Pace reached the conclusion that a good estimate of the marginal effect of the spatial economics model can be obtained either under a misspecification of the spatial weight matrix. This result is true under the assumption that all other components of the regression model are well specified. That is not always the case, especially in empirical situation. And among the possible sources that lead the result of Kesagen Pace not too old, we can mention the misspecification of the covariate X due to measurement bias, wrong source of covariate. We can mention also spatial heterogeneity of the regression parameter, beta or lambda. Whatever is the source of the spatial heterogeneity of coefficients, this possibility cannot be rejected, and the presence of both spatial autocorrelation and spatial heterogeneity should be considered as the most general case in many empirical situations. If we consider all possible DGP with a linear model plus spatial autocorrelation of endogenous plus spatial heterogeneity of coefficient, we get the 9 following DGP here. So here, when you have beta with coordinates, it indicates that it's a spatially varying coefficient. And we can mention all this model, and we introduce this notation, and JWR SAR 0. First term, it indicates if lambda is constant over space or spatially varying. The second is the number of constant beta, and the last term is the number of spatially varying beta. For example, this case is the SAR model. So, how to estimate this model? So we both look at the literature and made some new proposals. I will not talk about the detail of the estimation procedure, but I will only sketch some of them in the list. For spatially varying coefficient, JWR for geographically weighted regression or mixed JWR, we can use local weighted least square. So you use local subsample to identify the different beta. When you introduce a varying lambda, we have just one estimator that has been proposed by Paez and Foturingen, where all parameters are spatially variated, lambda and beta, but you have also all the different combinations in which lambda can be constant over space, but some beta are constant or spatially varying, and when lambda is spatially varying. All these models imply mixed JWR and are not available at the moment for estimating this model. So figure out how it can be, how we can estimate such model, we can mention the following feature of the estimator. Generally, the choice of the bandwidth parameter and the kernel type. So you use a spatial move from coordinates to identify local subsample, and you identify bandwidth and kernels, so the neighboring, using cross-validation criteria. To combine constant and spatially varying coefficient, there is a two-step method from May and Methodological also that allow to identify mixed JWR. And for the spatial photoregressive parameter lambda, that can be local or global, you can use local 2SLS or best 2SLS, or you can also use maximum likelihood or GMM. When W is unknown, we can estimate W using a sort of moment estimator that allows to identify in the SAR case the W that minimize the residual sum of square. And for the talk of today, we consider three types of kernel types that define the possible way to construct W and local subsample. It's bit square kernel, k-nearest neighbor, and adaptive bit square. Adaptive bit square is just a kernel in which you have a k-nearest neighbor, and the weight depends on the distance. So, since there exists no test in literature that can detect the presence of both spatial heterogeneity and spatial autocorrelation for this model, we need to resort to Monte Carlo experiments for exploring performance in terms of robustness of this estimator on the different DGP. So we ran 1,000 Monte Carlo experiments for these 9 DGP, and we draw a model with 3 covariates. The first covariate, X1, is normal random without spatial autocorrelation, and we use X2 drawn for a normal random with spatial autocorrelation and a variable that can be potentially misspecified. In fact, we take the Macmillan 2012 proposition for drawing this parameter. So we have some parameters that are independent for coordinate and one that is dependent of coordinates. Location are random, and we use a unique spatial weight matrix W based on 4 nearest neighbors for this experiments. Here you have the spatial pattern of the coefficient. So we have a concentric, monocentric spatial pattern with different center, and we have 2 planes, 2 opposite planes. This is the spatial pattern of lambda. Okay, so spatial autocorrelation is related to this spatial pattern. Here you have the value of parameter. So we choose a single mean value for lambda that can range from low spatial autocorrelation to high spatial autocorrelation. And here you have the value for the different beta. And when, depending on the DGP, the beta is supposed to be constant, we keep the mean. Here you have the result of the marginal effects. So we report only marginal effect, mean square error for marginal effects with no specification for X1 with W known. So as expected, we have in red the minimum best, first best. In green, you have second best. And in yellow background, you have the supposed to be more robust estimate. What we can see with X1 that is independent from coordinate, we have also for almost all estimator. Here you have the DGP, here you have the estimator. So we run all combination. We found the diagonal for X1, and we found that the spatially autocorrelated where SAR model with lambda that is constant and beta that could be all variables or some variables, some constant, are a good candidate for X1 for when you don't know what type of model you are using, what type of DGP you are confronted. When you use we choose the marginal effect of X2, so you have no specification, but X2 is dependent on the coordinates. It has several impacts, in fact, of the performance. And what is really interesting is that mixed JWR and JWR are affected by the simple fact that the covariate is spatially correlated. In fact, in all papers, you found only simulation with pure random of covariates, but never, I found no paper with covariates that is spatially correlated and what is the impact on local regression. Here, this second result shows that this model is quite interesting. When we introduce misspecification of X2 variables, so a moderate misspecification, we confirm we have almost no effect on the evaluation of X1. We have the same for the marginal effect on X1, we get the same results, but for X2, we show that model with lambda that is spatially varying allow to have a better identification of this parameter, and in fact it seems that the fact that W can change over space allow to correct the misspecification, partly correct the misspecification of X2. But at the end, when you sum all the marginal effect for all the variables, this one seems the more robust. So it's for this experiment, the good candidate is this one with you allow beta to vary over space, but not lambda. Here with the result with I will pass this part. 1 minute on the result with unknown. The simulation is still running, but we get a small experiment for today. We draw a random choice of DGP between this DGP and random choice of the kernel type and the bandwidth that allow to construct W. So we have an endogenous W, we don't know W, and we use our algorithm to identify W. And here we have the result depending on the specification. What we obtain is that we have a good percentage of recognition of DGP and kernel type. So it identifies that it's carnivores or B-square kernel or an additive B-square. And fine bandwidth here, you have also good results depending on this 52 is dependent on the fact that all DGP have no, some DGP have no bandwidth. So, what we obtain is that we need at least 2,000 observations to obtain this result, and we have really promising results if we increase the size of the sample. So, our algorithm seems interesting to identify W with the SAR model. And here you have the decomposition depending on the DGP in the experiment. In fact, we saw that we are very, the bad results come from JWR and mixed JWR that are very difficult to identify. But for SAR, as soon as you have spatial autocorrelation, we have very good results to identify the DGP. And I will finish on a comparison with the paper of Basil and al. 2014 that consider another way of introducing spatial covariate model, spatial varying coefficient model, but using a GAM model. In fact, GAM model allow to have some parameters that vary over space. And they propose to introduce dependence of the endogenous using not ID method but control function approach proposed by London and Powell. And their proposition is quite interesting because GAN is very flexible, you can do a lot of things, it's quite fast. And using same data, comparable formula, and we compare our estimator to the proposition. Thanks for the author to share the code. And what we get is here with Luca country database on twice. Here you have the result of Basil and Al with the sum of square here, with zero sum of square, and here you have the result of our model with the same W as Basil and Al, and with the automatic identified W. We get better residuals, but with not the same degree of freedom, so it's more fair to compare AK criteria. And we reach better AK criteria. To go here to better comparison, we have to compare outsample prediction with the model proposition of Basil. But the problem is that doing outsample prediction with control function is more complicated, in fact, because you have a two-step approach with residuals, and if you have residuals, you have no residuals for prediction. And to conclude, we have to finish the paper. We have to introduce a spatial Gaussian model in the estimation framework. It's quite easy. We have to improve the algorithm for identifying DGP in two ways. To adapt G-test to improve model specification with endogenous W. I hope that you will help us to do that, and we can propose in this package some function to identify for G-test and to make available this function. And we have to implement bootstrap tests for distinguish between constant and spatially varying coefficient, because we found that asymptotic tests that are proposed in local regression model are very dependent of the fact that the locations are not clustered. In fact, if you have clustered data, these tests are not good. And if you have spatially correlated covariates, also these tests are good. So we have to implement bootstrap tests.
Well, thank you very much. So we can
Thank you, because I did not prepare any slides, but I have two comments. One is related to the results that you presented, and another one is related to what parts you did not present. I'm confused, but first of all, you're using the leading squared error of the marginal effects, right?
Yeah.
And did you also consider using some other criteria? Because, for example, what would be also interesting is the precision of the estimated in terms of standard errors. For example, is the marginal effect significant? So, did you consider this, or?
No, not at the time, because here we have all marginal effects are very significant. And what is appear also that it's a gymnastic because you have root mean square error of a mean square error. Because when you have spatially varying coefficient, you have already a lot of parameters at the scale of your replication. You have to compute at this scale and at the global scale. So we keep on very simple things, just relative for the moment.
Okay, good. And then another point was you presented us the result of the best IDS.
Yes, I also mentioned all these results are based on the best 2SLS method, not 2SLS.
Yeah.
Yeah.
And
So,
you used in the paper, I mean, you used up to the fourth leg of the you used WX, W squared X, and W to the power of 3, right?
yes.
So somehow, isn't it the fact
more order. In fact, you increase your precision when you increase your number.
Yes, on the other hand, you also increase your muscle size. If you use more instruments, or did you test them that they are when they contribute, that they are not in the
I'm not sure to understand.
Okay, because I would say that maybe if you have too many instruments, there could be a bias.
Yeah.
So that's why I was thinking that maybe, this is driving also the big difference in the mean time estimate and the finishing and focus estimate. But if you say that you needed these many instruments,
Yes. In this, we have very, more accurate result with the first. With 4, it had nothing, and we have in fact very different with 2 and 1, and with more errors in the moment.
because I did something similar and then I found out that it was not so different if I just, that it was a big difference because the small space less, but that it was very big difference in whatever the first value.
Maybe just one last question if there is after we have to be on time. No? Okay? So thank you very much. So the last speaker is Michaela from Zurich Polytechnic School. So the title of the presentation is Estimation on the effect of time comparing variables in special panel data model, special Taylor variance, and the discussants will be Arna.
Yeah. Bonjour and welcome everyone to the presentation on time invariant variables. So time invariant variables are important in empirical studies. For example, if you want to estimate an earnings equality, then gender or race is of importance. Or if you want to investigate bilateral trade flows between two countries, then their distance to each other or whether they are sharing a common border or a common language are important. Or another example, which is also very prominent in spatial econometrics, is if you look at the text session behavior of municipalities, because then also distance and common border are important. So if you have non-spatial in your candle data model, what can you do? Unfortunately, you cannot apply fixed effects estimation because you cancel out the time invariant. Random effects would be in principle possible, but as soon as you have a correlation between the regressor and the unobserved heterogeneity, you have biased estimates. Something which is very prominent in applied work is the so-called Nunberg approach. In some textbooks, it's also mentioned the correlated random effects approach. In this approach, you just include the individual-specific mean of time-varying variables to control for the unobserved heterogeneity. And another approach is the Hausmann and Taylor approach, which I want to elaborate in greater detail. This estimator allows us to get parameters on both time-varying and time-invariant variables. It partitions the regressors into exogenous and endogenous ones. And the endogenous time-varying variables serve as instruments for endogenous time-invariant variables. And the original estimator was derived from the research. How about spatial linear candidate models? There I wrote 2 papers together with Vadi Bartage and Peter Egger, actually on the Hausmann-Taylor estimator, which only allowed for spatial correlation in the error. And also, we also have a spatial Montague approach developed by Nicolas, and he investigated spatial correlation in the dependent variable and the figure. So in this paper here, I want to present some spatial autoregressive Hausmann and Taylor variants. I want to estimate time-invariant and time-varying variables in a model with spatial correlation in the dependent variable. I want to allow for endogeneity of some of the regressors. In the paper also incorporated spatial correlation in the error. However, this estimator is very restrictive. It relies on many assumptions. And so I tried to relax one of this. And actually, right now I allow for an endogenous spatial weight matrix. Monte Carlo simulations show that this works well in small samples. And a small empirical illustration shows that it is useful for applying. So the outline of the presentation. First, I will present the spatial autoregressive Hausmann-Taylor estimator, then some Monte Carlo simulations, a small illustration, then the extension, and then I will conclude with some remarks and then so this is here the model. Here we have the spatial dependent variable. Individual units are denoted by I, the time by T. And X denotes our time varying regressors, and Z here denotes time invariant regressors. Here the subindex U denotes that they are uncorrelated with the unobserved heterogeneity mu, and the C denotes that they are correlated. And the final goal is we want to find estimators for lambda and the beta and the gamma. Of course, we need some assumptions. So this assumption is just straightforward. This is just the assumption that W is non-statistical Grosser normalized, that the lambda should lie between -1 and +1, and that this matrix here should be inverted. Then the second assumption is just that the regressors have full column range and that they are uncorrelated with the idiosyncratic element. And now here, these are the Hausmann and Taylor assumptions. So they contain the partition into exogenous and endogenous variables, and they also contain one order condition of identification here. And this means that we need to have at least as many exogenous time varying variables as we have endogenous time varying. So here we get the Hausmann and Taylor instrument set. Q denotes the within transformation matrix, Q1 the between transformation matrix. And the instrument set works as follows. This is are the instruments for the exogenous time varying variables, and they just instrument themselves. Here, these are the instruments for the endogenous time varying variables, the within transform guys. ZU instruments itself, and this here are the instruments that are used for the endogenous time invariant variable, and that's why we need this order condition, because we need to have at least as many XU as we have endogenous time invariant. And this is the Hausmann-Taylor instrument set for endogenous and exogenous time varying and time invariant variables. However, here also we have a spatial electric variable. And then the last assumption, this is just Homo's elasticity assumption of the error. I took this as a departure from the model. So now we have a four-step estimation procedure. This is the equation. So in the first step, we estimate here the variables in blue. So we estimate the time varying variables. Then in the second step, we estimate the time invariant variables. In the third step, we take account of the error term structure here. And then we conduct an efficiency enhancing transformation. Then we transform the model. And in the last step, we estimate the transformed model in one step. So in the first step, we apply the standard within transformation of the model, where this expression here, the Q0W, is still endogenous. That's why we apply a spatial autoregressive mixed effect estimator, which is just an NRV estimator. Where we use here the spatially left x's in within transformed fashion as instruments for the spatially left. Using this, we can calculate the residuals, and these are an estimate for this expression here. These are averaged, and then actually we get the regression equation for the second part, where again our ZC is correlated. So here we can apply a two-stage least squares estimator, where here we use the XU in between transformed fashion and the instrument for the ZC. And so we get consistent estimates after both steps, but they are not efficient. However, we can get a consistent estimate of the residuals, and this we can use in the step 3. This is just the variance-covariance matrix under Homo's elasticity and mu, and we can calculate these green expressions just by standard textbook formula, can apply the standard random effects Fuller and Matisse transformation by multiplying the model by this expression, and then get our transform. However, here we still have these three sources of endogeneity, and so we first subsume all the regressors, and then we estimate it in one step, where here we have our final instrument set, where here use the within transformed WXs as instrument for the spatially dependent variable, and the Hausmann and Taylor instrument set to account for the other endogenous frequencies. Yeah, this estimate is asymptotically normal distributed. Okay, now how does it work in practice? I look at some Monte Carlo simulations. Here again, the model under consideration. I have 3 time-derived variables. 2 of them are exogenous, 1 is endogenous. 3 time-invariant variables. All of them have the same parameter estimate. I mean, are 0.5, and yeah, my errors are uniform. W is Rosov normalized between 5 and 4, 5 and 9 neighborhood structures. I look at 4 different lambda values, and I compare it with spatial autoregressive fixed effects, random effects, and spatial number. And I look at the bias, frequency squared error, and the test size of an hypothesis test, whether the estimator equals its true value. I look at 2 sample sizes and did 100 applications, so here are the results. So let's first look at the fixed effects results. They perform pretty well, both in bias, root mean squared error, and also test size, but unfortunately here we don't have time-invariant variables. In contrast, the random effects estimator here is heavily biased. And this holds both for the time varying and the time invariant variable. However, if we do the Mundlag approach, then we can see that actually this estimator performs pretty well, especially here when it comes to the endogenous time varying variable. We have a nice test size and also the root mean squared error is small. However, if we look at our endogenous time invariant variables, then we see that it does not perform very well. In contrast, the Hausmann and Taylor estimator here has a good performance for both the endogenous time invariant variable, the endogenous time varying variable, and also here, our lambda. I mean, the results for -0.4 are similar, so I will just skip to the bigger sample size. And here we see what we would expect. The consistent estimators, fixed effects, and Hausmann-Taylor improve, while the other, which are inconsistent, get even worse or remain bad. So now I want to turn to a little empirical application. This is from the well-known example from Cornwall and Ruppert, who use data from the chemostatic income dynamics. Why did I choose this example? Because the data is quite old. Well, this is the standard example. If in textbooks the Hausmann and Taylor estimator is explained, and also these authors were among the first who applied this estimator. So here I just used the regression specification and especially also their variables and their partition into exogenous and endogenous ones, but I just added a spatial vector. And I just want to highlight some results. For example, here we see that the spatial autocorrelation parameter is highly significant and positive, indicating that it's important to be included in this example. The other parameter estimates differ slightly in size, but the most striking finding here is found for the variable female, which is insignificant with the normal Hausmann-Taylor estimator, but more plausibly negative and highly significant with the spatial autoregressive estimator. And also the coefficient of education is high. Okay, now I want to turn to my little extension, actually because, as I already mentioned, my estimator relies on many assumptions. And one assumption which is very frequently criticized, especially from non-spatial econometricians, is that we assume an exogenous spatial economics. And so I tried to work on this, and actually I follow here the approach from Q and Lee, where the endogeneity is modeled via a second equation. This is actually the cross-sectional paper, and I just try to attempt to bring this and to adapt this into my section. So here, this is the model. We have a second equation here. And F just denotes some time varying regressors. And here, geographical distance, and this additional variable D. I mean, D is not geographical distance. Maybe my label is not so good. This is just another variable, and the distance and this variable D affect value. And correlation of the errors of both equations cause heterogeneity of W. This is exactly what we heard today. And the goal here is to find estimators for the beta, the lambda, and the gamma, and the energy. include this expression here as a control function in the second equation, and we get this expression here. The error term is also slightly different. And now, how do we proceed? Now our step 1 consists of 2 steps, because first we have to estimate the theta here in one step. Then in step B, we can plug this in and estimate the other time variables. Step 2 is actually exactly as before. In step 3, we account for the error term structure, and in step 4, we estimate the transformed model again in one step. So in fact, step 1, step 3, and step 4 need to be adapted. Okay, here we just estimate the first equation of fixed effects, calculate here the control function, plug it into the second equation. So now we don't have a correlation of the errors of both equations anymore. And the indigeneity is accounted for of W, but this expression here is still endogenous due to the fact that we have WY. But here we can again apply the spatial autoregressive fixed effect estimator and get estimates for the time varying variables. We calculate again the residuals, and then step 2 is estimation. Okay, the error now is different than before. This is familiar. This we had before. This expression we get because we apply the control function approach, and this we get because we don't use the true theta, we use an estimate of theta. And these two expressions here are subsumed to theta because at the end, I mean, we cannot really distinguish these two parts because at the end we just get an estimate theta. And if I calculate the variance covariance matrix of this, I get this expression, and again, these components here can be estimated using our previous result from step 1a, or here from step 2. And then at the end, I transform my model, and again estimate the transformed model, where now I additionally have to include here the control function in my instruments. And I also did some Monte Carlo simulations on this. I will just go briefly over it. The regresses of the first equations are standard normal. They have this true parameter value. Time varying and time invariant variables are exactly as before. Here again, I have this another error term structure where the correlation is 0.5. The spatial weight matrix now consists of 2 components. One's the one thing related to D, and this is just my distance. Again, I use for the distance of 5 before, 5 behind. And then here I use this expression. And afterwards, this matrix is Rosson normalized. Again, I look at bias, root squared error, and test size. Yeah, and here these are the results. Actually, the same we saw this morning. Actually, if I erroneously use a spatial autoregressive Hausmann-Taylor estimator where I assume that W is exogenous, here I have bias and a very bad test size. However, if I use the other approach where I account for this endogeneity, the bias disappears and also my test size is better. But actually the other parameters are not so much effective. Like this endogeneity, however, the lambda. Okay, so now in this paper, I just wanted to show you how to estimate time invariant variables in an SAR pendulum model. Showed you some Monte Carlo simulations and a small empirical illustration. And the first results of this extension. Actually, in the paper, I also incorporated spatial error correlation, and I also conducted a test for appropriateness of the SAR-HT estimator. However, as I said, there are still many assumptions, and I tried to relax some of them. For example, there's no need to assume a spatial form of the correlation in the error. We could just assume spatial correlation of unknown form. Then I would just run the 4th step of the procedure and calculate spatial hack. Or one could think about avoiding the random effects error assumptions at all. We formulate step 1 and step 2 as moment conditions, stack them, and apply G. That's my presentation. Thank you.
Okay, thank you very much.
I really like this paper. Well, the one important point that we already know, which this paper makes again, is that the Hausman-Taylor 1981 structure is very versatile. It can handle a lot of things with modifications, and here, so of course, Kyla has explained very well what it does. Was this paper significant? Well, it adds substantial new features to the model. What does it add? She didn't talk about spatial error correlation, but she adds that. Spatial lag dependence, and importantly, endogenous spatial errors. Okay? So that really enhances, kind of within the Hausman-Taylor structure quite a lot of things. Okay, one thing which is important to note is that here identification, estimation, is based on many moment conditions. Many moment conditions. Therefore, my following comments, these are my comments. First of all, I have a question. So potentially I have a large number of instruments. In some ways, this reminds me of the days of dynamic panel data models with new moment conditions and lots of moments. So I suspect something similar is perhaps going on here. So do we care about instrument validity or identifying restrictions? Weak instrument problems? Remember that the point where we started coming here, and which Michaela explains very nicely in the paper, is from Honore and Pessina, where they pointed out inconsistency of the parameters of some of the parameters in the presence of time non-time varying variables. Now, in adding such a lot of moment conditions and therefore instrumental variables, and instrumental variables are bias estimators are biased in limited samples, so are we adding to the bias or are we reducing the bias? So that is what we want to know. So that is my first question. I have a couple of other comments. One is that the assumptions are at quite a high level. So one has to write down for the users what really this means, when one can make the assumptions, when one cannot. So, but that is a writing question. And my other comment would be, what about strong dependence and common factors? We had quite a bit of discussion regarding that. That is actually, from a practical point of view, quite an important issue. So, maybe with minor modifications, again, the Hausman-Taylor will be able to sort that out. Thank you.
Okay, so regarding the large number of instruments, you're right. I have many instruments, and depending, of course, how many exogenous and endogenous time variance time variables I have. And this is different, and I agree, I should do a test on this. At least also, this would also be very beneficial for the instrument application.
I think tests are just available over the shelf in Stata. So, kind of, it's just now.
Okay. So regarding the paper with Honore, this was a completely different, this was different because it was fully non-spatial and it dealt with nonlinear panel data models, and there actually we just combined, the first step was always a fixed sequence estimator, and in the second step we did some other estimator, depending really on the model, because for some models we had to impose stronger assumptions and for others less. I mean, the advantage is actually over that paper is, in the other paper we had very strong assumptions. I mean, because in the other paper we partly assume that all of the z's are uncorrelated with the unobserved Georgian. So here I just assume that some of the z's are uncorrelated. Yeah, the assumptions are at a high level, that's true. That's actually also something which I mentioned at the end, that I really want to work on this, and yeah, and also, I mean, the idea of the paper is really to provide something for the applied user who wants to estimate time variables under various forms of spectral correlation, that he can find this in the paper, and yeah, and you're right, I should write more on that and actually think more on that. And thank you for the comment about the common factors, because I thought it was
Yeah, please.
I saw you second step. The first step is to fix the track. Yes, to fix the track. And then the second step is to an IV, if it's important as well, so environment part. Did you test for anti-resistance? I thought, am I right? You get the second step estimator for the time invariant coefficients.
Yeah.
What's the real conversion?
Actually, I didn't calculate this at the end, I used just the arrow, and then afterwards I did this transformation, and then I calculated just the asymptotic distribution of the whole estimator after step 4. I didn't calculate the asymptotic distributions for the separate steps.
But when you, because you have the individual effect eventually an observed one, that's the mu, right? You treat as a random, right? The mu I,
Yeah.
you treat as a random variable, right?
The UI? This is time invariant, yeah.
But you treat it as a random variable. In the second stage,
No,
no?
no. In the second stage, actually,
That's unobserved, mu I is unobserved.
UI is unobserved, yes, but I use this Hausmann and Taylor assumption where they say that the endogenous time invariant variable can be instrumented by the exogenous time varying variable. And that's what I used in step 2. I mean, this is an idea.
But I never see the way of converting those coefficients can be square root nt. I only see square root n. Because you collapse the time, to get those individual coefficients, time invariant, you basically is a between equation. When you panel data, you can get within and between. This is a between variation across the units over time, average. So you get only an observation.
Yeah, that's true, but I use I don't calculate the standard errors based on this step 2. I calculate it based on step 4. So where I just, estimate 1, 2 stages square estimation where I use instruments for all of the variables.
Yeah, but if even I know all these time, the coefficients of the time varying coefficients are known, only thing I don't know about will be the time invariant coefficients. And I can, instead of doing all this style, I guess you think residual,
Yeah, you could just
I mean, that's the best I can get is square root n consistent.
Yeah.
It cannot be square root nt.
Okay, yeah. If I would just stick with step 1 and step 2,
Mhm.
and then estimate step 1, and calculate the standard errors for step 1, and then step 2, and estimate the standard errors of step 2, yeah, then I would do that, yeah. I mean, if I would not like to do this high-level assumptions on this error, and then I would just stop after step 2, yeah, then you're right. I would just
How can you get step 4 improving the efficiency? That's my problem. I improve the rate of converting. To me, it's impossible.
It's impossible. So maybe I have to elaborate it.
Because you're just exploring the fixed effect part is getting of this kind of variable. And the one left out the information that perpendicular to this time the deviation variable. So that's all you have. And how can you get, you have n observations across the unit. The time has collapsed. So that's the
No, but not at the end. Not in step 4.
no, the mu I, if the mu I disappear, then okay, because that is a random variable. Hang on for everybody, and you have an observation. Yeah, the other term is always mu I random. If you don't have mu I, okay, no problem because the noise is only the value become very small proportional to.
Yeah, but if I estimate all things in one step, I calculate one asymptotic distribution.
And you don't get the square entity. You can maximize it. You don't get square entity for those coefficients.
But I will just get them for the time right. Or for not.
I'm not sure whether this can help or not, and just a quick thought. You said it, you are using the instrument, Hoffman Taylor instrument, for the individual specific. So my understanding is that you have translate n parameters into a fixed number of variables. Then the number of parameters being reduced instead of n of them being reduced to a few. So in that sense, probably you're able to get a number to the NT consistent.
You don't get. I think you are coming to play because you play that too.
Okay.
And I don't think it's right. It's a square and consistent.
Okay.
Yes, sure. Yeah, if your mu I is gone, then I think it's square and. But if your mu I is not, then you cannot get that.
but you said that you use the
And
data
based
set
on
of
this,
combined
yeah.
grouper, which is so thank you very much. Thank you very much.
The first is no, first, I suggest.